All right. We've already done, another cylinder. We've already done the cylinder, right? We can slice it into a bunch of pieces and find the volume, right? We did it with the rectangular prism, slice it into a bunch of pieces. Okay, those ones are easy because I don't really need to slice it into a bunch of pieces. Even if I slice it into like, I don't know, let's say 2 pieces, took my rectangular prism, sliced it in 2 and found the volume of each of them and added them together, that would be the volume, wouldn't it? Right? Because these are all, every cross section of it is exactly the same. Would you all agree? Okay, easy enough to do that. Okay. Same with the cylinder, each cross section is exactly the same. All right. What do we have here? Y'all see the cone at home?
Yes.
Ooh, the cone. Okay, here's my cone. I'm going to hold it perfectly horizontally. I'm going to slice it vertically. Open it up. What are the cross sections? Circles. Now, is this circle on the base of it here the same size as the next circle when I slice it? No, it's bigger than the one that I get when I slice it, right? And then the next one is a little smaller, and then the next one is a little smaller, and the next one is a little smaller. Okay. In this case, if I sliced it in half, I don't really have a good formula to find the volume of like that piece of that cone. I mean, there is a formula for it, but you probably don't know the formula for like the truncated cone volume, probably not. You probably don't know that formula, do you? For a truncated cone. But we could approximate the volume of a piece of it by just taking the volume or taking the area of this first base and multiplying it by how long I cut off. And then I could do that with the next slice and the next slice and the next slice and the next slice over like, let's say 10 slices of it. And I would get an approximation for the volume of this cone, right? Because every cross section is this circle, right? So we should be able to do that. And would that be a okay approximation for the cone? Maybe. It wouldn't be great, but it wouldn't be horrible, right? And we did that. If we think back, and I'm going to write on the board here for a second, we're gonna come back to the cone. We think back to when we were trying to find the area underneath a curve. Remember when we were trying to find the area underneath the curve? There's my curve. And I said, let me draw some rectangles, right? Remember we drew a bunch of rectangles? And I said something like, okay, let's figure out the area of each of those rectangles and add them together. And that's an approximation for the area under the curve. And then we said, well, what if I make, instead of 5 rectangles, I make 100 rectangles. I get a better area, right? If I make 1,000 or 1,000,000, I get a really good area. Right? That was one of the sort of like important concepts that we were talking about with integration. Right? Is that we wanted to make an infinite number of rectangles. Well, same concept is going to apply with our cone. Right? We're going to take this cone, we're going to slice it, an infinite number of times. Right? So we're going to slice it an infinite number of times, and each of those cross sections that we get is going to be circular, right? And it's going to have a tiny little thickness to it. Right? And we're going to take the area of the cross section, multiply it by the thickness, and get a very, very tiny volume for a little circular cross section, and then sum all of those together infinitely. And that should give me the volume of the full cone. Does that make sense to you guys here? Yeah. People at home, does that make sense?
Yeah.
Yeah? Okay. Good. Cones, very exciting. Do you know the area of the circle formula? Yeah, pi r squared, right? So we should be able to find the area of that base and then multiply it by that base. Now, if I held my cone this way, horizontally, and I slice it, what is the thickness of that? What direction is it going in, the thickness of it? It's in a, is it in an up-down or in a left-right direction? It's in a left-right direction, right? The thickness of each of these pieces is in a left-right direction. So if I think about this, I'm going to draw on the board again. If I think about this, here's my cone. Here's the first cross section. There's the next one that's a little smaller, and the next one that's a little smaller, and the next one, and the next one, and the next one. And I'm putting all of these little pieces together until it looks like a cone, sort of, right? And each of these things has a thickness in the x direction. Everybody agree? It's in the left-right direction, the x direction. So we've sliced this vertically to give a thickness in the x direction. And that thickness in the x direction is very, 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 very small. It's infinitesimally thin. Okay? And when we have an infinitesimally small change in the x direction, what do we usually use to represent that in calculus? What? Okay, well, we sometimes use the delta. We started with the delta x, and then when we converted the delta x from, remember we did like the limit as n approaches infinity of all of that stuff with the f of x sub k times delta x. When we converted that into our integral notation, what did we turn the delta x into?
dx.
We turned it exactly into the dx. Right? This is a thickness of dx. So what we're going to do effectively for all these cool little weird shapes, and not the cone is not a cool weird shape. The cone is easy. All right, we're going to deal with cool weird shapes in a minute. But what we're going to do is we're going to find the area of the cross section, multiply it by that thickness, which is just dx, and then we're going to integrate across the length of whatever the shape we're looking at is. So we're going to take whatever shape we have, slice it into an infinite number of little pieces, find the area of the cross section of each one, multiply it by the thickness dx, and add all of those things together using an integral, sum them using an integral. And that's going to give us the full volume of any shape that we want, as long as each cross section is the same basic shape. Like it works, works really nicely, especially if you have a cylinder and every cross section is exactly the same. That's great. But we should be able to use it for any shape as long as the cross sections are uniform. They're all circles, or they're all ellipses, or they're all equilateral triangles, or they're all squares, or they're all, what have you. Any as long as they're all the same shape, even if the size of them changes. Does that make sense? Yeah. People at home, does that make sense?
Yes.
Yes.
Like that. I mean, I think, isn't that neat? Okay. That's the truncated cone to show that there's an ellipse. That's not what I wanted to grab. I wanted this one. Pyramid. Triangular pyramid. Ooh. Everybody see the triangular pyramid? Same concept. Can we do that with this? Every cross section is a triangle. It's an equilateral triangle. If I can find the area of that equilateral triangle, I can find the thickness. I can add them all together using an integral. Right? Doesn't matter what the shape is. Triangular prism, that's fine right there. They're all the same cross section. That's obvious. Where's my other pyramid? There's my other pyramid. Square pyramid. Square pyramid. Square pyramid. Square cross sections. Find the area of the square. Write a generic formula for the area of the square. Multiply it by the thickness. Sum them all together. That's what we're going to do. Conceptually, okay? Now, here's the part where it gets more complicated. Oh, here's a fun one. Now, change my mind. Here's the part where it gets more complicated. Sometimes the base of your object, and this is not perfect. Somebody 3D printed this for me because I would have trouble explaining what these things look like to people. Sometimes the base of your object is going to be something weird. Like this is not something that you know the area of or anything, right? It's supposed to be a parabola because we have whatever 3D printers here at the school. This is supposed to be a parabola. That's the base of this solid. Parabola. So it sits on the parabola, right? Sitting on the parabola. What is the cross section? Is a triangle. Everybody at home see that the cross section is a triangle?
Yes.
Yes.
Base parabola. Sitting on the parabola. If you slice it, you get triangles. Okay? So we get this sort of weird looking shape. And so they've put together a fair number of triangles, pieces that were attached together as they did this. And so this is like having, you can see, it's like having an infinite number of triangle cross sections. Okay? This is not some regular shape that we would deal with. So just imagine that this is fully curved here, not have all these little ridges on it, right? And that this is like a flat curved face on each side of it, right? We're going to look at shapes like this that are totally irregular. regular, that we don't just have a formula. Like, you know, the volume of my cone, 1/3 pi r squared h. Right? I mean, you may or may not know that, whatever. My cylinder, pi r squared h. Easy, right? All these are easy. There's formulas for them. But there is not a formula for a parabola as the base with cross sections that are equilateral triangles. Right? Or we might have one with a parabola for the base and cross sections that are squares. Or, you know, a sine curve, part of a sine curve is the base, and the cross sections are isosceles right triangles, or what have you. All kinds of weird shapes. That's what we're going to be looking for the volume. Right? So we're going to be less concerned about these easy, regular pieces that we are able to deal with formulas, and more concerned about these weird looking ones like this. Okay. So good, conceptually good. We're going to slice into a million pieces, take those cross sections out of it. All good. People at home, does that generally make conceptual sense?
Yes.
Yes. All right. That's our goal. It's not as bad as it might sound. I don't know, maybe it doesn't sound bad. Hopefully it doesn't sound bad, but it shouldn't be too horrible. We've got to do a couple of things each time. First off, we're going to have to figure out in which direction the thickness is, because sometimes the thickness may be in the y direction, in which case we'll have to integrate in terms of y. And the problem and how it's worded will tell us if it's going to be done in terms of x or in terms of y. It won't specifically say do it in terms of x, but based on what it says, you'll be able to figure that out. And then we will have to know formulas for the areas of each of the cross sections. And that's about all we're going to really have to do. And we're going to piece it together into an integral, then we'll integrate and do the calculus part and solve. Sound good? All right, let's give it a try. People at home, are you ready to give it a try?
Yes.
One person. Good. Okay. All right. We're going to start with the base of a solid is the region between 2 root sine x and the x-axis, between 0 and pi. And we are going to have cross sections that are squares. And those squares are going to go from the x-axis to the curve. We want to find the volume of this weird solid. I'll give you guys a second to write it down while I sketch the graph of 2 root sine x that you probably don't know what it looks like. 2 root sine x from 0 to pi literally looks very similar to just sine x. Right? From 0 to pi, there's not much difference other than it's a little bit steep. That's 2 root sine x. I'm giving the people here in class a second to write it down. So I don't know if those of you at home are doing it digitally or have it written down already or also are waiting or whatever. It's really cool if I get my toolbar to show up so I can change colors because then things look a little better. But I think that's just wishful thinking today. Tools. Shut up. Amazing. No, we didn't look at the circle. We're gonna look at the lacrosse ball. Same with the lacrosse ball. Slice the lacrosse ball. What do we get? We get circles. Right? You guys quit the lacrosse team, right? Yeah. I heard they had a big win yesterday. And they beat the #1 team in the state. Yeah. Like beat them. Like destroyed them. Did they? You weren't good. I was gonna say, think how much better they'd be if you were all still playing, but all right. So we all ready? Y'all got this written down now? Okay. So we got this is the base of our solid. This is 2 root sine x, and we have cross sections run from the x-axis to the curve, and they are square. So going from the x-axis to the curve, and then coming out of this screen or the board or whatever, straight at you, is a bunch of, well, square cross sections here. Just like we had all those triangular cross sections from this little red thing. So you can also think of the board in front of you here in class or your screen, if it's just flat on the ground, like the coordinate axis is just flat on the ground, and coming straight up out of the ground or off of the paper is a bunch of square cross sections, just like this, right? Has a bunch of triangular cross sections coming straight up off of the base. Everybody good with that? Y'all, everybody here seems okay. At home, are you okay with that?
Yeah.
That the actual shapes of these are sort of hard to visualize. And even if you can't visualize them, and it's hard to visualize them, you should still be able to go through and be able to set them up properly. If anybody's in engineering and wants to 3D print me more stuff, that'd be cool.
Sure.
What?
Sure. Yeah.
Sure.
Just give me the equation.
What?
I can 3D print you more stuff if you want.
Perfect. I don't know who's talking to me, but who's talking to me?
Me.
Nice. Sid.
Sid?
Yeah, that's Sid.
All right. We'll talk later. We'll talk later. You can 3D print me everything. That'd be great. Yeah, that'd be good. Okay. So here's our setup. We want to find the volume. So in order to find this volume, first off, we have to determine whether we're going to use X or Y as our variables. Okay. So if we're looking at this in terms of the thickness of it, where is the infinitesimally thin thickness? Which direction is it moving? Is it going up and down, or is it going left and right? Should be going left and right, right? Up and down, no, this is like the whole length of this square. Right? That's actually got some length to it. In fact, it goes up here at the max, it goes all the way up to a length of 2, right? Because that's 2 root sine x. But the thickness is in this x direction. So we're going to say the thickness of each of these cross sections is dx, which means that everything we have to do in this problem has to be done in terms of x. It means my limits of integration and the area formula that goes inside the integral have to be in terms of x. Okay? So we're going to integrate something dx. Now we'll start off with, from where to where should we be integrating? We're going to start here at 0. We're going to go here to pi. Right? So we're going to integrate from 0 to pi, the x values. And we need to then come up with a formula for the area of each of these squares. Well, first off, what's the area of a square? The base times the height, right? It's the base square, the height square, the length square, or whatever you want to call it, right? It's just one side of it square. Well, I'm going to write up the area equals the side length squared. What is the side length? Yeah,
The height from the x-axis to the sine curve?
Right, exactly. It's just the x-axis to the function 2 root sine x. It's just whatever the y value is. And the y value is 2 root sine x. So we should be able to write this as 2 root sine x squared. Okay. We're going to say S is equal to y. So our area is the y squared, and y is 2 root sine x. That set up okay with everybody here? And at home? Anybody have any questions on that?
All good.
What?
All good.
All right. Wonderful. Okay. So now let's figure out this integral. What's 2 root sine x squared? Two squared is 4. And so it's just 4 sine x, right? What can I do with the 4? If it's just a constant in there, I can pull it out and I don't have to worry about it. So I'm going to write this as 4 times the integral from 0 to pi of sine of x. Good? Any questions? Any questions there at home? All right, what's the integral of sine of x? Should be negative cosine x from 0 to pi. So this becomes 4 times negative cosine pi minus negative cosine 0. And what is the cosine of pi? What? No. Cosine of pi is -1. So we've got -1, that should be positive 1. And then what's the cosine of 0? 1. So we have minus -1, so plus 1. We got 4 times 2, 8. Good or no? Any issues or questions or problems with any of that? Anybody? People at home, you okay? Y'all alive?
Yep, you're alive.
Alive. Any issues with the problem?
I have a question again.
You have a question. What's your question?
So if we were to put like the orange parabola triangle shape on the coordinate plane, would we just see the parabola because the parabola is the base?
I'm not sure what you mean.
Like on the graph, we can see 2 root sine x because that's the base for this problem. But if we were to put the orange shape,
If I were to put this thing there?
yeah.
Yeah. The base is that parabola. So it'd be, you'd see the parabola as the base, and then you'd see these cross sections that were triangles sticking out at you.
Okay,
Then
good.
the triangles would look like the squares that I have drawn on the screen, and then.
Got it. Okay, thank you.
Yep. Everybody else good?
Yes.
Yes.
Wonderful. Has anybody watched any of the lecture videos from this quarter? No. Have any of you watched the lecture videos from this quarter?
No.
Okay. Nah, never mind then. All right. Let's see if we can do this same function, but instead of squares, we have equilateral triangles as the cross section. So more similar to the one we were dealing with, or one we were looking at with the 3D printing earlier. Cross sections are equilateral triangles. So first off, we know it's going to just look very similar. There's our 2 root sine x, and the cross sections are now equilateral triangles coming straight out of the screen or straight out the page, right at you. So, is anything going to change with the limits of integration? Is the dx going to change? Is the area of the cross-section formula going to change? Yes. All right. Now, you may or may not know the generic formula for the area of an equilateral triangle. I know you know the formula for the area of a triangle, right? 1/2 base times height. Yeah. But there is a specific formula for any equilateral triangle that will be very useful for you to know. I suggest you write this down. The area of an equilateral triangle is side squared times √3 divided by 4. Okay. That will be helpful. Equilateral triangles come up from time to time, every year or two, on the AP test. And so if you know that formula and it shows up, life will be good for you. S squared √3 over 4. Okay, so you want to know that. Now, that means that our formula in here is S squared √3 over 4. But I can't integrate S squared √3 over 4 dx because the S and the X don't match up. So I got to write the side in terms of X. And we should be able to do that because what's the side length? It's just the distance from the x-axis to our function. Right? So S is just, again, going to be 2 root sine X. Good or no? Everybody here good? Everybody at home good?
Good.
All right. So let's do this. We've got an integral from 0 to pi. I'm going to pull my constants out, and as I square s, I'm going to get a 4. True. That 4 will cancel with this 4 in the denominator, and I can pull the root 3 out. We're going to get root 3. We're just going to get sine x. And we already did the integral of sine x. We know what that is. It's negative cosine x from 0 to pi. And in fact, we already evaluated negative cosine x from 0 to pi. That was not 8, it was 2, right? We had a 4 out from 4. So this is just 2. Everybody good there? Everybody at home good?
Yes.
Okay. These are a couple of fairly easy examples. We're going to make it more complicated. Integrals are going to get more difficult. Everybody in class here is good? Nobody at home? No questions? All right. We've got a paperweight. That's about all these weird shapes are good for. Paperweight. And we got a paperweight. Its base is the region between 2 sine x and the x-axis, 1 arch of that sine curve. What do we got? Semicircles as our cross section. It says those cross sections are going to be cut perpendicular to the x-axis. So let's draw out 2 sine x. Looks about the same. From 0 to, well, where is the cross factor? Where is that first arch of 2 sine x at? What? It is pi. Pi, 0 to pi. And now it says cross sections cut perpendicular to the x-axis. So we want to slice it this way and get semicircles if we open it up. So that means that the thickness is going to be in which direction? Should still be in the x direction, right? The thickness of each of those is still in the x direction. Let's draw some semicircles on there. Here's a semicircle. That's not really a very good semicircle. Semicircle, right? Coming out of the page. So we know that we need to integrate from 0 to pi. And what's the formula for the area of a semicircle? Pi squared. Semicircle, half of that circle. Pi r squared over 2. And we already said we're doing it in terms of x, right? The thickness is dx. So we want to integrate from 0 to pi r squared over 2 dx. Can I integrate pi r squared over 2 dx? Nope, because r and x don't match up. I need to make the r in terms of x. I did? I probably did. I don't know. I say a lot of things and then I forget most of them. I don't know. I probably did. How do we find r for this semicircle? Not quite. Yeah. So what we've got here is actually a diameter, isn't it? And that's the diameter of the semicircle. You guys at home agree with that? Did you guys see the green okay? Yeah. Doesn't show very well on my laptop screen. You guys can see the green okay? Yeah. Okay. All right. So the diameter is this whole height from 0 to 2 sine x, which means that my radius is just sine. So what we're going to do is let's pull the constant out of pi r squared over 2. What's the constant in there? The pi over 2. We'll pull the pi over 2 out. We'll integrate still from 0 to pi. And now it's just r squared, and r is sine x, so it should just be sine squared. Everybody good with that? Now, we've got to deal with integrating sine squared. Integrating sine is easy. Integrating sine squared is a little bit more difficult. There's no good u substitution to use for it. There is one good way that we should be able to do it in Calc 1. In Calc 2, you could do some other fun stuff and integrate sine squared x, but we don't know that stuff yet. So anybody remember? I think we did one or two of these similar to like sine squared or cosine squared back in the first time we met in like quarter 2. Not the first time, but like in quarter 2. Anybody remember how to integrate sine squared? Anybody at home? Sine squared. So in the other documents folder of the Google Drive is a paper titled Required Trigonometric Identities. And on that paper, there is a way to convert sine squared x into something else that we will be able to integrate. No, that is something you could convert sine squared into. It is sine squared equals 1 minus cosine squared. But that becomes an issue because we still don't know how to integrate cosine squared. So, and converting it back to sine squared, that won't help. So
is it the 1/2 times 1 minus cosine 2x?
it is 1/2 of 1 minus cosine 2x. It is the power reducing formula. And it may, on the required trig sheet, you guys have somebody have that sheet in front of them. See people flipping furiously through their notebook. Yeah, it's in there. Yeah. Oh no, that's not the one. Yeah, Melanie. Yeah, that's the one. Philip, it's on that one also, Philip. But it's yeah, that's a different sheet, but it's also on that. You see it on there? It says power reducing formula. Yeah. It says sine squared x equals 1/2 of 1 minus cosine 2. And this is good because it gets rid of the power, and the power is a pain for us to deal with. Oh, sorry. I just wrote pi. Sorry. Thank you. And now I can pull the 1/2 that's inside of there out, can't I? If I wanted to. And I'd just be left with 1 minus cosine 2x. And to integrate 1 dx should be easy. But to integrate cosine 2x will require us to use a u substitution. So my recommendation, I have 2 recommendations here. Recommendation number 1 is to learn how to do these simple u substitutions. Just figure out how to do them in your head real quickly. Right? Just be able to do the u equals 2x and then throw in the 2 and the 1/2 and work through it on your own in your head. Because that's going to be, especially for anybody that's going to take Calc 2, like that's going to be important that you're able to do that. If you can't do those in your head, you're really going to struggle in Calc 2 when you get into something called integration by parts. You really want to be able to do those in your head. But if you're not planning on taking Calc 2, you don't necessarily need to worry about doing them in your head. I mean, it'll be helpful, it'll make life easier. But if you have a piece of something that requires a u sub and a piece of something that doesn't require a u sub, separate them into 2 different intervals if you're not just able to do the u sub in your head. Okay? Everybody good there? Okay. So I'm going to do that. I'm going to pull the 1/2 out. 0 to pi. And I'm going to write this as 1 dx minus the integral 0 to pi of cosine 2. Yeah. That's separated into the 2 different integrals. And cosine 2x to integrate that, we've got to let u equal 2x and du will be 2. Everybody agree with that? So we're going to throw in the 2 to give us a 2 dx, but if I put in the 2, I'm going to have to put in a 1/2 also. So now it gets a little complicated because there's like my brackets with my constant out in front of everything, and then there's a constant in front of one of the integrals, and it's a little bit messy, but it shouldn't be too horrible, I hope. So we'll go to the next page to finish this up. We're still going to have a pi over 4 out in front. And then we had the integral of 1, right? We had an integral of 1. What was the integral of 1?
X.
X. Yeah, X. From 0 to pi. And then what do we have? The second part of it is going to turn into 1/2 the integral of cosine u du. And we're going to have to be careful with our limits of integration. We'll deal with those in a second. So it's minus 1/2 the integral of cosine u du. And previously, we had a 0 as the lower limit, and u was 2x, so 2 times 0 still leaves us as 0. But in the top, we had pi as our limit, and so what does that upper limit need to become?
2 pi.
To become 2 pi. And so now we're ready to evaluate the first part, remembering that pi over 4, this problem is not going to actually matter, but that pi over 4 is applied to both of those integrals. Okay? So we got pi over 4 times x at pi is pi, and x at 0 is 0. And then we've got minus 1/2 the integral of cosine, which is sine. So we're going to evaluate sine from 0 to 2 pi. Everybody good there? Everybody at home all right?
Yep.
Wonderful. All right. Pi minus 0 is just pi. And then what's this? We got 1/2 of sine of 2 pi minus sine of 0. And with any luck, we know that the sine of 2 pi is 0, and that the sine of 0 is 0. So I've got pi minus 1/2 of 0, and 1/2 of 0 is 0. And pi minus 0 is pi. So we've got pi times pi over 4, which is pi squared over 4. And I believe this one had units attached to it, so we'll put our units on it as inches cubed. Any questions on that? Either Zoom people questions or people here in class questions?
Wait, so on the AP test, this would be a free response question?
Most likely, yes, this could be a free response question on the AP test. Yes.
Oh,
Generally, we're going to get talking about what the free response questions look like by early next week and early to mid next week. But this would be, this is probably a little more difficult than you might expect on a free response. Probably a little more difficult. But this whole process would be like one piece of one of the free response questions. There are 6 free response questions that you have an hour and a half for. We'll talk about the breakdown of that all in a bit. Not today, but next week. And this would be like 1/3 of one of those questions. So you'd probably have like 5 minutes to do something like this, except it'd be a little bit easier of an interval. That help? Does that answer your question, sort of?
yeah, thank you.
Yep. Cool. All right. Everyone here good? You have another question? Okay. Well, you'd still use u equals 2x. So if I was trying to do the U substitution in my head, what I would do, so I have the integral from 0, what was it, 0 to pi, right? So cosine 2x. If I'm trying to do that in my head, I'm just going to say, okay, I know that u is 2x, and that means that I need to put a 2 in to get my 2 dx, which means that I know that my final answer has to have a 1/2 attached to it. So I would just say, okay, this would become 1/2, and then I know that it's cosine u, so the integral of cosine is sine, so I just be like, all right, now sine u. Well, what was my u? My u was 2x, so it's 1/2 sine 2. Like the integral of, and then I would be able to leave it at 0 to pi, and I don't have to change the limits because I've in my head brought it back to being 2x. Does that make, that's what I mean. And the more of these that you do, the more you'll get used to it. Like the integral of cosine 2x is 1/2 sine 2x. The integral of cosine 7x is 1/7 of sine 7x. Right? There's lots of them that, you know, if you look at the integral of e to the 3x, it's 1/3 e to the 3x. Right? So yeah, that helps. Does that answer your question? Oh, yeah, no, you wouldn't do it different. I would just, you know, if I was doing like this, I was doing this, and I didn't want to have to separate. I'd just be like, okay, I just separately do the cosine 2x. This is x minus 1/2 sine 2. Good. People at home, good? Good?
Yep.
All right, this is the last one we're going to do today here. And then if I'm hoping we'd have time to go over some of the limits multiple choice. If we don't, that'll be the first thing we do tomorrow. Okay. I'll give you guys a second to write this one down. Try and write this one down, draw a little picture of it, and see if then we'll work through it together because it's a little different. But at least write it down and try and draw your own picture. If there's no reason to record while you're doing it. All right, so x squared plus y squared equals what? Circle. Right, radius of 1 centered at the origin. And cross sections of this are perpendicular to the y-axis this time, which means that we should be drawing these isosceles right triangles as if they were going perpendicular to the y-axis. Right? And so we've got, imagine again that the board is just like flat on the ground. I think that makes this one look a little easier. If the board is flat on the ground or your screen is flat on the ground, this is the paper with the triangles coming straight up off of it into the air. Yeah? This is the one that always actually sort of looks okay to me when I draw it. Everybody good with that at home? Right here?
Yes.
Wonderful. All right. So what is our integral going to look like? We're going to need to do this one in terms of y, because the thickness of each of these is in the y direction. It's in the up-down direction rather than the left-right direction. And left to right, it's stretching all the way across here. It's not infinitesimally thin in the y direction, but it is, or in the x direction, but it is in the y. We're going to integrate the y. We know what the area of a cross section is, right? Because these are just isosceles right triangles. That should be 1/2 of this leg squared. And where are we going to integrate from? Yeah. And we want to make an important note that, and you don't have to write the y equals, but I'm going to just for like the instruction's sake here, that we are integrating in terms of y. We are going from the bottom, y equals -1, to the top, y equals +1. Not from x equals -1 to x equals positive. Just to be sure about that. Okay? The only thing we have left to do is to put our full integral, our integrand, into terms of y, which turns L into terms of y. So how are we going to do that? If L is this, right? That's that. Okay, let's convert it to some form of x first. How are we going to convert it into x? What is starting from here to here? What is that distance? What? It's x. That's x. You all agree that's x? How do we measure an x value? We measure it from the y-axis to the right. Okay? Now these are isosceles right triangles, and they are sitting on a circle. If I draw this is called a chord, right? This is the chord of the circle. If I draw a chord from one point to the other point that is directly horizontal, and the y-axis should cut it perfectly in half, shouldn't it? So the right-hand side is x. The left-hand side should also be x. So L ought to be 2x. Okay, cool. So what is L squared? So we have L squared. Without a 4x squared. Okay, cool. So let's move forward with this thing. We're going to turn into y in a second. We're now looking at y equals -1 to y equals 1. We have the half times the L squared. The half times the 4 is just going to be a 2. And we're going to have an x squared in here. But it's now it's x squared dy, which is still not okay, right? We still need to turn it in terms of y. So how are we going to turn x squared into y? We have the circle equation. What is x squared equal? 1 minus y squared. Exactly. Everybody at home good with that?
Yes.
Wonderful. So here is our integral to represent this volume. 2 times the integral from -1 to 1 of 1 minus y squared dy. Everybody okay with that?
Yes.
All right, let's integrate. We got 2. Integral of 1 is y. Integral of minus y squared is minus y cubed over 3. And we'll go from -1 to 1. Now it's just arithmetic. Plug in the 1. 1 minus a third. Plug in the -1. -1 plus a third. And let's see, we got 1 minus 1/3 is 2/3. And then we're going to add 1 to that. That should be 5/3. And then we're going to subtract a third. That should be 4/3. So we got 2 times 4/3, which should be 8. Good or no? Yeah. All right. That is the basic area of volume using known cross-sectional areas. We knew the cross-section of the area there, the isosceles right triangle. We knew it for the circle or the semicircle we did. We knew it for the square. We knew it for the equilateral triangle. We know the area, the cross-sectional area. We just use it and sum together an infinite number of them. At home, are we good?
Yes.
Wonderful. Anybody at home have questions or anybody here have questions? All right. We got like 5 minutes left. I think we will probably not start with the multiple choice review, unless anybody's going to be devastated about that. Anybody devastated if we wait till tomorrow for the multiple choice review of the limits and the derivatives? Okay. Now, up in Google Drive, I posted this morning is a document called volume of known cross section or volume using cross sections or something like that. The assignment is there. My answer key is already up there with it also. I would be happy to answer questions on that tomorrow as well, but we're going to start with the multiple choice. We will have a quiz on Friday. The quiz on Friday will solely be on what we just did today. Okay. We will have, I may give you a different type of cross section. Maybe we'll have a rectangle or something really fancy like that. But I suggest that you look over the notes from this and look over the assignment and do all the problems on the assignment, because the quiz will look just like some of those problems. So tomorrow, number 1, limits review of the multiple choice. Number 2, derivatives multiple choice review. Number 3, questions from the homework, and then number 4, we'll move on with more volume stuff if we have time. Sound good to everybody? All right. Those of you that are Zoom people from your house, if you don't have questions, you can go.